Okay, good afternoon, everybody. I hope you're all enjoying the conference so far. Okay, so in preparing this presentation, I'm making two assumptions. Firstly, that is you're trying to write a nice brand new project, greenfield, there's no legacy code to worry about, which, though that's probably not realistic in most cases, it means that then you can just think about things from a fresh perspective and then look at things. Is there something here that I can then integrate into existing code? And secondly, you've got a nice, shiny C++20 compiler and library. GCC 10 and 11 have been out for a bit, and most of the stuff is supported in those. So it's not out of reach. Obviously, Visual Studio also supports lots of stuff. So yeah, it's not out of reach if you're targeting any of the major platforms. So hopefully, you can be able to make use of some of this stuff. Okay, so I'm going to sort of divide this up into three things. Firstly, we're going to look at how you choose your concurrency model. And then we're going to look at actually starting and managing some threads, and then the C++20 facilities for synchronizing your data. So if you're choosing your concurrency model, then fundamentally, you need to decide what it is that you're targeting. Are you, using concurrency in order to provide some form of separation of concerns between the different aspects of your application that can potentially run concurrently? You want them to all proceed, and if you were doing it all on a single thread, you'd have to interleave the code. And so by splitting it out into separate threads, you're separating your concerns. And that can make some of your code simpler. And the other option is that you might be using it for scalability. You've got some form of hardware that you're targeting. Even if it's desktop PC, you're thinking our customers are now running 16 cores on their desktop PCs or their laptops, and we want to take advantage of that. Or maybe you're targeting an HPC rack with thousands and thousands or maybe millions of cores. And you really, really want to take advantage of that. And depending on which of these aspects you're looking to, then that will guide the way that you use the C++20 facilities and guide the way that you look at your program. So these choices inform how we structure things. So if you're looking at scalability, then Amdahl's law is key. This is something you're really going to be focused on. You're going to be looking at what is the parallel scale-up that I'm going to be getting? How much of my work can be parallelized, and how many processes have I got to do this work? So you're looking at your speed-up multiplier, and we have our fraction here. So if the number of processes goes large, then this number on the bottom is going to be quite small, and 1 divided by a quite small number is quite large. On the other hand, if the fraction of parallel code goes low, I have 0 amount of my code can be run in parallel, well, then we're just going to get 1 divided by 1, so no scale up at all. And in most realistic cases, there's going to be some sort of scale off there. You're going to have some fraction of your code can be parallelized, and you're going to have some number of processes that's greater than 1. Otherwise, why are you looking at scalability? So we're going to see some form of speed up here. But actually, if we start putting some numbers in, then you'll see that really the important part of this is actually this fraction here. What percentage of your code can be parallelized? If we say 90% of our code in our application can be parallelized, then we think that seems quite high without any prior knowledge. 90% seems reasonably good. So what happens if we start seeing numbers in? We've got 1,000 processes and 90% of our code being parallelized. We get a whopping 9.9 times speed up. That is not very good out of 1,000 processes. You might have been hoping for maybe worst case a few hundred times speed up. So that 90% is really hurting us here. And you can see that if we stick in 100,000 processes. We've increased from 9.9 to 9.999. We haven't even got to 10 times yet faster, and we've got 100,000 processes. The fact that 10% of our code has to be serialized is really, really hurting us. So if you're after scalability, this is what you're looking for. You're looking for making sure that you eliminate serial dependencies in your code. You know, if you start pushing up the percentages to 99%, then on our 100,000 processors, we still don't get to 100 times speed up, but we're doing much better. And if you're looking at this at parallelism, you know, trying for this scalability, then one of the things you can do is you can reach for the standard library itself and just say, use the standard parallel algorithms. Because for those of you that were in Bryce's talk about things yesterday, then for big data sets, then the capability of the compiler and library to actually scale things is really good. And particularly if you do have hardware that's dedicated to it, like you have a GPU that's really good at processing big floating point data sets. And to do that, you just stick in standard execution par as the first parameter. This gives the compiler and the library the ability to parallelize if it knows how to for your data set. And so if scalability is what you're after, then this is probably the easiest way to get it. But obviously, you need to make sure that your compiler and library are, have that facility for your target data set sizes. And if you try and do sorts of 100 elements, it's probably not going to parallelize it. 100 billion, probably it will, if it knows how. And again, that can depend on your compiler settings. So, for example, GCC, without any settings, may probably choose to do things serially, whereas you have to put the right flags in to say, yes, use the TBB library, then it knows how to parallelize things. So you have to be aware of making sure you're using your compiler to enable that. Again, something else that Bryce pointed out yesterday is that consecutive calls to your parallel algorithm actually have a serialization step in between. So if you do a transform and then you do a reduce, then the transform can be nicely parallel, but then it has to wait for the transform to finish, and then it can start doing the reduce as a separate step. Again, hopefully in parallel, good scalability, but we have that step. So whereas if you use the combined transform reduce, we don't have that serialization step in between, and therefore you reduce the serial fraction of your code and increase the ability of your program to make use of the scalability of your hardware. It's not just simple combined algorithms like transform reduce. Again, as Bryce showed us yesterday, then there's ways that you can combine things using straightforward transform and to combine multiple steps as part of the function object that you provide to enhance the parallelism. But you have to actually really look at the problem you're trying to solve to decide how to do that. Okay, so the other thing you might do if you're looking at parallelism and scalability is use a thread pool. And so you split your task up into lots and lots of independent tasks. Obviously, the parallel algorithms will do this for you. So if your work fits with those, then use those and let the compiler and library do it. They've already debugged this. On the other hand, if your tasks don't naturally fit like that, then you can use a thread pool. You can divide your work. You create a thread pool. You then execute your work on the thread pool, and the thread pool implementation will take care of dividing that between the CPUs and making sure that each CPU has work to do. At the moment, we don't have a standard thread pool. When we have the P2300 executors, then hopefully we will get a thread pool implementation that goes with that will then quickly spread out to the major implementations. But for now, you're looking at third-party thread pools. Again, TBB provides such a thing, or HPX likewise. If, on the other hand, you're not looking at scalability as your sole reason for parallelism and concurrency, you're looking at separation of concerns, then you're saying, well, actually, the raw performance is not such a priority. See, we're hoping for a gain, but that's not the primary focus. And so we don't have to worry so much about can we get the most out of our hardware. Instead, you're looking at what things can potentially be run in parallel, run concurrently. If I've got a GUI application, maybe the the printing can be run as a background thread. And that saves the main thread from having to worry about interleaving printing operations. Or in a word processor, you might have a spell check running as a background thread. Various things. Now, you might be downloading from the internet in the background thread. So these are tasks that can run concurrently. And by separating the concerns and moving them out to background threads, then you are making the implementation of each of these tasks simpler, because each task is focused on exactly what it needs to do. There's less shared state because it's not having to communicate the ongoing status with the other parts of the application, aside from perhaps literally a status flag and how far through am I done, so you can update the GUI. And so this can make our code simpler, but we have to watch out for those cases where there is communication. So if we have long-running tasks, then you probably don't want to put them on a thread pool, because then they occupy one of the thread pool threads permanently or for a significant chunk of time of your application, and it limits the scope of the thread pool to manage the execution of any other tasks. So if they've got a long-running task as part of your application, you probably do want to create a dedicated thread. And so we can use Jthread for that. This is the new C++20 type for managing threads. And you can just, you can pass in the tasks. And here I've just got lambdas for passing in. So run the GUI stuff on its own thread. Run the printing stuff on its own thread. So if you're going to be doing these dedicated threads, then you're going to need to know how to start them. But before we do that, I'm going to have a sort of sidetrack into cooperative cancellation. So everybody's used GUIs with cancel buttons. I do something and it pops up a progress bar and it says, this is going to take 3 days and 57 minutes. You think, oh, okay, fine, click cancel. Maybe I'll do that another time. And so we're all used to having a background task that we want to cancel. But it's not just GUIs that need it. No, sometimes then you're running a command line, you hit Control-C, you want it to actually cancel things. Or even within an application, then you might start doing some process and then as part of the application logic, then you decide, actually, no, that process that I started doesn't need to happen because something else has changed. No, I was doing a background spell check and the user typed some more words. So I need to interrupt what they're doing, what the spell check is doing, and make sure that it reflects the new state of the text that it's checking. Or in a compiler's IDE, it's got a background compilation to highlight in red underline all the mistakes you currently made, or where there's a clang tidy improvement that it can suggest. And you type in some new code and it needs to stop running clang tidy and restart with the updated code. Most platform thread libraries provide some means of killing a thread. The C++ standard doesn't, but we're all running on some platform and there's some way of killing a thread. But that's really, really a nasty thing to do, and it leaves your application in an unknown sort of state. So we don't want to do that. What we want to do is say, this task that you're running, can we stop it, please? Ask nicely, as a cooperative interruption. And this is what the C++20 standard finally provides us. This has been in discussion in the committee for about 10 years before it finally became standardized. And the final form that it makes is we have stop source, which is a source of stop requests, and a stop token, which you can use to query, have someone ask me to stop. And again, it's purely cooperative. If somebody makes a stop request but you don't actually check it, then nothing happens. The flag is set, but if there's nobody checking it, does it really make a difference? So the standard usage model for this is we create a stop source. You then get a stop token from your stop source. You pass your stop token to whatever task it is that you wish to interrupt. Then, at some point, you will call request stop on the stop source. And this sets the flag. And that's all it does. It sets the flag. But having set the flag, then the task that has got the stop token can then check the flag. And at some point during its execution, you expect that it will check the flag. And it will call stop requested to see, has somebody asked me to stop? And then if it returns true that the flag is set, then you expect it to do something meaningful to cancel the operation. Obviously, if you don't, you can check the flag and then discard it, in which case, why did you bother check? Or you can check the flag and say, yeah, well, I will stop the request, but in a minute, there's this other thing I want to do first. And that's okay. You know the logic of your application. You know where it's sensible to make this check and what operations it should be doing when you do. But the point is that it's there. You can check whether somebody has asked you to stop and then interrupt your own code if that request has been made. So just to reiterate, if you do not check, then this is purely cooperative, so nothing happens. There's nothing automatic about the stopping. So what does that look like in code? Well, we have our stoppable function that takes a token, and it calls stop requested periodically, every time it round its while loop. And whilst you haven't asked it to stop, it's going to do some stuff. And then on the other hand, we have a thread that's going to stop this. It takes the stop source, and then whilst it's not done whatever it is that it thinks needs to happen, then it's going to do something. And then when it's finished, whatever that was, it's going to say, no, request stop to ask the other thread to finish up. And at this point, then the stop requested at the top here will return true, and so our stoppable function will exit. See how fast that happens depends on how long do stuff takes to execute. If it's a many second operation in and of itself, then it will be many seconds before that's responded to. Is there a question? So the other thing that you can do is that you can say, I don't want to have to check this flag all the time, but I do have another mechanism by which the operation I'm doing can be interrupted. Those of you who are here in Daniela's talk this morning will have seen her use of stop callback in her kill me function, where you use the stop callback to cancel some outstanding tasks. And in that case, it was I/O and things that were processing like that. We had closing I/O handles. And again, so you take your stop token and you construct your stop callback. And then you say, well, what happens? When somebody requests stop, I want them to do something that's going to interrupt me. And we pass in a little function here, or in this case, a lambda, that's going to actually do the interruption. So we've got our async I/O, we've got an open file function that returns us a file handle. And the I/O library we're using says, you can interrupt this operation by calling cancel I/O, given the handle. It knows nothing about stop tokens in and of itself, but this stop callback allows us to say, when you request that our operation stops, then call cancel I/O on this handle, because this is the operation that's being interrupted. And so we've got keep here a reference to the handle, and we cancel the I/O on that handle. And so if somebody calls request stop whilst we're doing some read data here, we're doing our I/O on the file, and it hasn't yet finished, then the call to request stop will then call cancel I/O, and yes, this runs in the thread that calls request stop. So it will cancel the I/O and it's all done. If on the other hand, then they don't request stop whilst it's processing, then when you hit the curly brace at the bottom, the callback is destroyed and it no longer needs to worry about cancelling the I/O. So the fact that this lambda holds a reference to the handle is okay because it's not dealt with once it goes out of scope. So this allows us to extend the cancellation mechanism with stop tokens to any library that we use that has its own method of interrupting. Because you can use stop callback to make sure you use the appropriate library-specific means of interruption. So this is my favorite part of the cancellation mechanisms. But you do have to be aware that this cancellation happens on the thread that requests stop. So you are injecting code into another thread. So you want to make sure this is as minimal as possible so that you're not upsetting any scheduling that's happening on that thread or any processing or suspending it for too long. Okay, so with that little digression, we can now move back on to starting and managing threads. If you're using C++20 and you're trying to manually manage threads, in 99%, if not more of cases, you want to use standard Jthread. There are other ways you can do it, but mostly you want to do this. If you really, really, really want to get to run your thread to get a specific result back, then you can use standard async, and that will give you a future that you can use to wait for the result and wait for the thread to finish. So you can use standard async. You could use just plain old standard thread, but really why? No, you should only use it if you have no other choice, probably because you don't have a C++20 library after all. And even then you should, if that is the case, then you should download Nikolai's implementation of Jthread from his GitHub account and use that. But mostly, you're going to be using Jthread. And the Jthread constructor starts the thread. This actually, it takes the callable thing that you supply and the function arguments you supply. It creates a new thread and runs that callable with the supplied arguments. With an addition. And this is why I did cancellation first, because we have this stop token. The Jthread provides us with a stop token. And it gives it to whatever function you call, if it will accept it. And if your function doesn't take a stop token, then it just doesn't give it to you. It does a compile time check. Does the function you provided accept a stop token as the first argument? If it does, it gives it to you. If it doesn't, then it doesn't. So in this sense, if you've used standard thread before, this really is a drop-in replacement, because it will just pass the supplied arguments in the same way that standard thread does if your function doesn't accept a stop token. So the basic API is not very big, really. No, we have a default constructor that creates an empty Jthread object with no thread. It's just like a null pointer. It has nothing to manage. Then we have a constructor that takes a callable and an optional arguments. And this creates a new stop source, and then it creates a new thread that runs the callable. And it will pass in the stop token to go with that stop source, if it supports it. Otherwise, it will just pass in the supplied arguments. The destructor, so whereas the standard thread destructor just kills your application if you've still got a running thread associated, the destructor of Jthread is much more sensible. And it says, well, you're trying to destroy the thread handle. So first of all, I'm going to actually say, this thread ought to be stopping now. So I'm going to request that it does stop. And then I'm going to wait for it to finish. And this means that it's much more clean. And from an exception safety point of view, if you've got some threads and something throws an exception, then it will interrupt those threads and then wait for them to finish, rather than potentially leave them dangling references to local code, or, as I said, terminating your application, as standard thread would do. We then also can get the ID of the thread, and we can manually wait for it to finish. So that's the basic level API. And it's a value type. It's a handle. It's movable. You can pass it around, which means you can store it in containers. So you can have vector of standard Jthread and use that. And I use that in lots of places for managing threads. If I've got a bunch of threads associated with, with some block of code, possibly in a test, possibly in production code where I've got a number of explicit background threads I'm managing, then you can just use a vector. And because we have this destruction, waiting and interruption, then if you don't finish populating your vector and something goes wrong, then it will interrupt the existing threads and wait for them to finish before it tidies up. So this all works nicely. And again, it's a value type, so you don't need to use new. I've seen so many people who are coming from Java and C# who write new standard thread of whatever to start their thread. Don't do that. I mean, aside from the fact that you shouldn't be using plain new anyway, then we don't need to allocate the Jthread object on the heap. We can just pass it round. It's a value type. So one important thing to note is that if you supply arguments, then you can't by default pass references to the callable. If you pass an argument a value you're thinking by reference, then it just takes a copy internally. So you can't easily pass non-copyable things. You need it does perfect forwarding. So if you call standard move on a movable thing and pass the R value reference as the argument, then it will move it into the internal storage rather than copying. But we are taking that copy, and this saves us from worrying about dangling pointers and dangling references to objects that are local to the thread that started, to the function that started the thread, and therefore saves us from race conditions. Obviously, you can use a lambda with a capture, with a reference capture in order to capture references, or you can explicitly use standard ref to pass a reference wrapper object. Or you can pass pointers, so obviously, because obviously copying the pointer doesn't copy the object. But by default, then this copying just gives us that little bit more safety. And it makes you think about whether or not you really do need a reference or a pointer to the object, or whether actually copying is good, because it means that that thread is then running with its own set of data rather than sharing that data with anything else. As I said, the destructor calls request stop and then joins. So if we have a stoppable function that's going to keep checking the flag and doing some stuff in the meantime, then if we have a Jthread that uses that, then when we hit the end of foo and we destroy the Jthread object, part of the closing brace, then it will call request stop, and so our thread function will be interrupted, because next time round it's while loop, it will check the flag, it will see the flag is true, it will finish. And so then the destructor will then wait for that, and it's all tidied up nicely. There's the thread doesn't continue running longer than the lifetime of the Jthread handle. So there's more to the cancellation support than just this call in the destructor. Like I said, we implicitly create this stop source, and you can manually get hold of the stop token by calling the get token function, which obviously the library does that automatically. It passes it as the first parameter to the callable, and but you can actually call it yourself directly. Destroying the Jthread calls request stop and joins. But of course, you still need to check the token. This is manual cooperative cancellation. Checking the token is something that you have to do if you want to be interrupted. And again, stop callback means that then you can use another interruption mechanism. If you're using a library that uses that. It makes a blocking call, but with a separate interruption mechanism, you can use stop callback to make that work. So like I said, you can get the stop token. There's a function for that. You can get the stop source as well, so you can manually request stop even without having to destroy your handle. Or you can just call request stop directly, because that is also exposed. So it really does, it provides you, the full set of operations on your cancellation API. If you are using threads that you are managing yourself, rather than using thread pools or parallelized algorithms, then you probably have some form of shared data that your threads are going to be accessing. In which case, you're going to be needing the C++ 20 synchronization facilities. Most things need some form of things. And the first thing to be aware of, if you've ever got any form of shared state, is data races are undefined behavior. A data race is where you have unsynchronized access to the same object from two threads, and one of them is modifying that object. They might both be modifying, or one's modifying and one's reading. Either way, it's a problem. And it doesn't, you might think, oh, but no, I know because I've put a wait in there. The first one happens, and then it waits 5 seconds before the other thread accesses. A wait does not do synchronization. It is still a data race. If you want synchronization, put a synchronization there. Use one of the facilities that I'm just going to be describing to actually make sure that there is synchronization. Because data races are undefined behavior, and your program can now do anything at all. The C++ standard imposes no requirements. It might accidentally format your hard disk. It might accidentally send an email to your boss. It might crash at the most inconvenient point and therefore cause somebody to die if it's automotive software or medical software that is keeping somebody alive. So you do not want data races. We need synchronization. In C++ 20, we have lots of synchronization mechanisms. We have latches. We have barriers. We have futures, mutexes, semaphores, and atomics. These are listed in the order in which I think you should reach for them. If you have a problem that can be solved with using a latch, use a latch. If you can't be done with a latch, but it could be done with a barrier, use that. Failing that, use a future. At this point, you're running out of high-level things, and now we're down to mutexes. But yes, use a mutex rather than a semaphore or an atomic. Atomics are a last resort synchronization mechanism. You use them when you are 100% sure you need them because you have profiled lots and you know that your synchronization is a bottleneck. So let's have a look at latches in C++ 20. They have the form of a standard latch. It's a single-use counter. When it hits 0, it is signaled, and it then stays signaled forever. And that signal provides synchronization. We create a latch with a non-zero count. As threads count down, then again, yeah, the thread gets to 0. You can explicitly wait for the latch to reach 0, and that can be on any thread that has access to the latch object. You can just call wait, and then you will be woken when the count reaches 0, and not before. So we have our API. We construct a latch with a count. We can count down. We can wait. Or you can combine the two and say, well, I'm going to count down and then wait for all the other threads that are calling countdown. So if you've got a bunch of threads that are working together to some aim, they've got a bunch of data that they're processing together, you might be waiting for them all to initialize and prepare appropriate bits of data, and then they all want to carry on with the remaining processing. So you call countdown and wait, call countdown and then call wait, or just arrive and wait as the combined operation. So if we put that in some code, we have our latch. I'm going to call it done. We create it with a thread count because we've got that many threads. we've got some data in a vector, which we've got one block of data per thread that we're trying to construct. And then we have our vector of Jthreads for managing the threads. So we construct our Jthreads. Each of them, it takes the loop counter by copy, because you don't want to have a reference to your loop counter, because otherwise you've got a data race. But other than that, we want to hold it by reference so that we can access the data vector. And we're going to construct the data for this thread, the particular block of data that we're processing here. And then we're going to count down the latch to say, I've done that, I've done the initialization. But then this thread's not going to terminate, it's going to keep going, it's got some more work to do. We don't know, for the purposes of example, we don't know what that is, but something meaningful that this thread has to do before it finishes. But the data is prepared. So we've count down our latch. And then on the main thread, we can wait for all those initializations to complete. We call wait on our latch, and it will wait until every thread has done its countdown. And at this point, we know that every thread has called make data, and the appropriate vector element has been populated. So then we can process the whole vector. And we know that now we are just reading from the data that has been prepared by the threads. And so we don't have a data race, we know that it's safe, and all the data is ready. We can just process that data fine. Because the call to do more stuff doesn't accept the data, so we know that that's not going to touch it. This is a really nice pattern to use for tests. If you're writing multi-threaded tests, then one of the things that makes it tricky is that starting threads is a big, slow operation. And so if you want to run a test that runs on multiple threads, and you're trying to have them all running together because you're wanting to check whether the synchronization happens correctly and things like that, then if you manually start them one at a time, which you don't really have much choice other than to do so, then sometimes if you haven't got any explicit synchronization in there around the test code, you can find that the first thread that you started has finished before the second thread has even started. Because these are short-run things, because it's a test that you're running. It's not a long-running application. You're just running a small thing in a test. And so by using a latch, then this makes it just that little bit easier for you, because the first thing that each thread can do, it can count down and then wait on that latch. And so when the last thread is ready, then that will then trigger the latch, and all of them can then do the test processing. And this means that all the threads are created and have started running and are now ready to run, apart from the fact they're waiting on the latch. And so if you've got enough CPUs in your system so they can all really, really run concurrently, then as soon as that last one starts and releases and triggers the latch, then all of them can now start running straight away. And this is the best way that that there is of controlling the scheduling of the threads in your test. Moving on from latches, if that doesn't meet your needs for your given application, then we try using a barrier instead. Barrier is a template. That provides a reusable barrier. And it is done in phases. Again, we construct, you don't need to specify the template parameters. There is a default template parameter. If you don't need the completion function feature, then you don't need to provide it. We construct a barrier with a non-zero count and possibly a completion function. You don't need to, like I said, you don't need to provide one. If you don't need it, then just don't. Right? Then one or more threads arrive at the barrier, and some of these threads will wait for the barrier, and some of them will say, no, I'm done. I don't want to wait for the barrier. I'm just doing this one time. But either way, when all the threads that were specified in the count have reached the barrier, then the barrier becomes signaled. At this point, it runs the completion function, if you provided one, and then loops and resets the count back to the maximum, and then waits again for the threads to arrive. So this is a loop synchronization. And the completion function allows you to provide something that happens in between the loops. So if you're processing a block of data on multiple threads and then at the end, then you want to publish it, ship it over the network, or put it on the screen, or whatever, or save it to a file, then that can happen in the completion function, because at that point, you know all the threads have done their processing, and they haven't yet started on the next block. So you can safely do this. It's run on one of the threads, but you don't know which one. And then, after the completion function is finished, then the count is reset, and all the threads wake up, and then they can carry on again. And like I said, not all the threads need to wait. If they don't need to wait, then having declared at once that they're not participating anymore, then they can't participate again. The count is permanently reduced by 1. So the first time round, if you had 5 threads, and the first time round one of them said, "I'm not going to wait, I'm going to drop," as the term is, then the next time round there's only a count of 4 because there's only 4 threads left. So you need to watch out for that if you try and use it. So the template parameter is the task type. Like I said, if you don't need this feature, then you don't need to specify a template parameter, and the default just works. And you pass in the initial count and the completion function task. You can arrive, which gives you a token, which you can then use to wait later. Or you can arrive and wait, or like I said, you can arrive and drop, which says, "I'm arriving, but this is the last time I'm arriving and I'm not going to wait." But it does still potentially trigger the completion function. And it does signal the barrier this time round. So like I said, they're great for loop synchronization. And the completion function allows you to do a little bit of serial processing. Again, if you are doing serial processing, this will hit your overall scalability performance, because that serial fraction really, really kills your scalability from Amdahl's law. But sometimes, if we're doing this, then maybe that's okay. Maybe we're just hoping for some gain over this little part of the application. But it allows us, we can pass the result to a file, pass it to another stage in the pipeline, or display things on the screen, or whatever is appropriate. It runs on one of the participating threads, but you don't know which thread that is going to be. There are standardization proposals which are discussing about being more lax in determining which thread it is, and giving the library far more scope to choose things. But really, because you don't know which thread it is, then there's nothing there that you can specifically rely on anyway. So if we look at it in some real code, then so we might use, say, a standard function as our task type. And then in this case, it's a void returning function with no parameters. So anything that you pass in that doesn't take parameters, you could use. And so we have our worker threads, some form of index to say which worker thread they are. Then we're going to loop. Again, we're going to use a stop token. Whilst we've not been asked to stop, we're going to do the stuff appropriate for our worker index. And then we're going to arrive and wait at the barrier. And then, so we'll have a number of these worker threads. And each worker thread will do the appropriate thing for its index. When they've all done on this batch of data, then they all arrive and wait. The last one will do the completion function to finish the task. And then they will all start again on the next element. And then at some point, obviously, someone will interrupt them, and then they will stop and not do any more processing. Okay, futures are next. Futures are a one-shot data transfer mechanism. They provide synchronization for a single blob of data from a producer to a consumer. And the producers come in 3 forms. We have a standard async, which wraps an execution of a task. You say, here is a function that when it's complete, it will give us a value. And that value is then stored in the future object, which is returned from the standard async call. We have standard promise, which just says, well, here is a handle to the data, and at some point I promise to provide you some data at some point, and you explicitly call a member function on the promise to provide that data. And then you can get a future that's associated with that promise, and then the consumer can then just wait for the data. And when the data is set via the promise, it becomes available to the consumer. And then we have package task, which again, it wraps a task. You give it a task, and it gives you, and you can get back from it a promise, a future that will hold the result of that task. But it doesn't ever run it. You have to explicitly invoke it. A package task is a callable object. And when you invoke it, you don't get a result yourself as the thread that's doing the invoking. The result is captured in the future, ready to be received by the consumer, which is somewhere separate. So you could use package tasks, say, in the implementation of a thread pool, where you wanted the code that posted tasks on the thread pool to be able to get results from those tasks. Because then you could then store a package task in your internal task queue, which is then invoked by the pool threads, and then the consumer gets the result. But your pool threads don't need to know what the details of the tasks that were actually stored are, what their task types are. So package task gives us a way of making them all the same, a bit like standard function does. And in any case, you get a standard future out. So we have our basic API for standard future. We have a default constructor which creates something with no data. You can check if it's valid. You can wait. You can wait for a period of time or until a time point, and you can get the data. If you call get, then it implicitly waits for it first. So you don't ever have to explicitly call wait if you don't want to. You can just call get, and that will do the waiting. So if we put that in some code, we have a blocking function that calls wait and then calls get. So as I said, you can omit the explicit call to wait if you'd like. Sometimes then that you can, if by putting both the wait and the get, then you can choose where in your code the waiting happens, and you can then put some extra processing between the wait and then the get if you so desire. Or you can wait for, you can pull it by just waiting for 0 seconds. I'm not going to wait at all, but is the data ready? Well, check the result. And if the data is ready, then you can then conditionally call get to actually read that data. And the synchronization is actually on the level of the wait. So when you wait for it, when the wait completes, then you know the data is ready, and that there is that synchronization path. So you can use it for waiting for other things too. So yeah, so promise has a default constructor, again, with creates an empty state. But in this case, then it's a empty state waiting for data that you can pass. And so having got, you've got the promise, you can then request its future, you can call get future here at the bottom to get the future associated with that. And you call set value and set exception to actually provide the data. Because the future can store an exception as well as, or rather instead of, the data of type T. In which case calling get will throw that exception rather than return the data. So they're movable, you can pass them around. So you can have a thread that's waiting on a future, so you move it in. We're using C++14 initialization for our Lambda here to move in the future. And then we're going to wait for the data and retrieve it and pass it to our function. On the other hand, we have another thread that's got, in this case, we're holding a reference to the promise. Again, we could have moved it in. Promises are movable. And then you're going to set the value with whatever the result of making that data is. You can, like I said, you can store exceptions. So you can set the exception to an exception pointer, which you can either construct manually using make exception pointer, or you can catch, catch ... and then use standard current exception to get your exception pointer. You can also use standard async. If you're using standard async, then you want to use this first parameter, standard launch async. this makes it start another thread. You can omit it, in which case it may or may not start another thread, or you can specify standard launch deferred, in which case it definitely won't start another thread. And if it doesn't start another thread, then it will actually run your supplied function when you call get on the returned future, which is really counterintuitive and can be confusing because your task doesn't actually run until you ask it for its value, in which case you might as well have just moved the code to the other thread and just called the function at that point. So if you're using async, you probably want to use standard launch async as the first parameter. And what you get back is a future. Now this has the additional bonus benefit that this future also contains a handle to the thread. And so it will wait for that thread to finish, as well as returning you the result of the function. And if you don't explicitly call get, then the destructor of the future will wait for the thread to finish. It's one shot, so you can't use it again. If you used a future channel once, then it's now done. It gave you the data. It's now not valid anymore. And if you try and call get the second time, it will throw not whatever stored the exception was, but an exception to indicate that there was that it was an invalid future. If you want the data multiple times, or you want to retrieve it in multiple places, use shared future, which you can just move a normal future into a shared future, or you can call explicitly share, which does that for you and gives you an appropriate shared future. And so then you can have two threads that capture the same shared future and both call get, and that works fine. Okay, so mutexes are our lower level locking mechanism, synchronization mechanism. They stand for mutual exclusion. They're a means of preventing concurrency, so you really don't want to use them too many places. We want to be sparing. We have 6 mutex types. I think that's 5 too many. What you should be using is standard mutex. If you get an urge to use any of the others, then really, really think hard and try and rethink your design so you don't, because most of the time they just add complexity to your code and make it harder to reason about and don't gain you any benefit. And in fact, possibly even they make your code a little bit slower because they've got additional code in there to deal with the complexities. So really, use standard mutex. Don't use anything else unless you really, really, really have to. And again, we have RAII types for locking and unlocking. Standard scoped lock is the one that you should be using all the time, apart from the very, very rare case where you're using a condition variable and you want standard unique lock. And they are, like I said, they're RAII types, so you just create a scope lock and you pass it the mutex, and it locks the mutex in the constructor. It then unlocks the mutex in the destructor, and you don't need to worry about exception safety or anything like that. If you try and lock multiple mutexes, you could put 2 scope locks side by side, but don't do that, because this is opening yourself up to a deadlock. If somebody tries to transfer money, in this case, between 2 accounts from A to B, and simultaneously another thread tries to transfer from B to A, then you're locking the same 2 mutexes in different orders on different threads, and that's a deadlock. So don't do that. Instead, just pass both mutexes to your scope lock and say, I want to lock these 2 mutexes. And the scope lock will take care of it for you. You don't need to worry about what order you pass them. It will sort it out. It will avoid deadlock. Do this if you really, really need to lock multiple mutexes. Hopefully you don't need to lock multiple mutexes, because that in itself is an indication that you haven't got a coherent set of data. But we really want to if you really need to, which maybe you've got fine-grained accounts like this, then use scope lock with two mutexes. So if you're waiting, then, well, how do you wait? You could busy wait, but please don't. No. You lock your mutex, you check if it's data, you then loop round, you unlock your mutex, you lock it again, you check the data. This is consuming CPU time and locking and unlocking your mutex a lot. Don't do that. And it potentially delays the notification anyway. So what we want to do is use condition variable instead, in which case you need a unique lock instead of scope lock, because you pass it to the condition variable wait, and then it will unlock the mutex whilst you're waiting. Tell it what you're waiting for. Provide this predicate function that tells what it's waiting for. And then notify it when the data's ready, and you can use scope lock on the notify side. So do that. And put these braces round. Unlock before you call notify. It makes it a little bit faster. If you were wanting to cancel and you had a busy wait, then you could just stick in a stop token. Standard condition variable doesn't support that. So you need to use standard condition variable any if you want stop tokens. In which case, then again, you pass it the token. In addition, you pass the lock and the token and the predicate. Semaphores are really flexible. They're a bit like mutexes, but with bigger counts. A binary semaphore 0 and 1 is almost identical to a mutex, except it doesn't fuss which thread you're on. Whereas a counting semaphore in general have a bigger count. You can acquire a value in which decreases the count, or you can release it, which increases it again. It doesn't care which thread touches it. So it's a bit like borrowing a book from a library. They don't care who gives them the book back, just that they got it back again. I recommend you read the little book of semaphores. If you're fussed about semaphores, it tells you how to do everything with semaphores, including mutexes, condition variables, whatever else. In C++20, a semaphore is a counting semaphore and possibly a specialization for a binary semaphore. We have acquire and release functions. And so you acquire it, you do something, and then you release it, possibly on a separate thread, depending what you're doing with your semaphore. Atomics are our lowest level. They are spelt as standard atomic of T. T must be trivially copyable and bitwise comparable. It still may or may not be lock-free, but this is what it is. Or T could be one of our smart pointers, standard shared pointer or standard weak pointer, because there's specializations for those. We've got various types. We know there's some that are guaranteed to be lock-free, atomic signed lock-free, atomic unsigned lock-free, and atomic flag. But we don't know how big those signed and unsigned integers are, so you probably just want to specify what sort of integer you want and rely on it being lock-free, or at least, or check with is always lock-free, static member function. So in summary, avoid managing your own threads if you can. Use parallel algorithms and thread pools. Use Jthread. Use stop token for cancellation. Use futures, latches, and barriers if you can. They are better than using mutexes. If you must, use a mutex. And if you really, really must, use an atomic, but try not to.